This is part two of energy resources, and today we're going to look at some of the various terms that are used in any energy production, especially in petroleum and oil and gas. So here's just a list of terms for you to commit to memory. You already know some of these, right? So you know what an anticline is, you know what a syncline is, you know what a basin is, and you know what a dome is. That is a structural basin and a structural dome. Now, porosity, you should know by now, but I'm not sure if you do or not. It's the space that's within rocks, sedimentary rocks in particular, that's in between the grains of that rock. And so there's a lot of different types of porosity, like fractures will give you porosity. If you can imagine, porosity is a medium in which you can actually fill it up with fluids of some sort, whether it's air or water, salt water, or natural gas and oil. And so that's why porosity is important to us today. Impermeable has to do with the fact that you sometimes can stop water from flowing if you have something to block it up, essentially. And so the opposite of impermeable is permeable. So permeable means that you can actually have fluids that will flow through a rock. So permeable fluids would be able to flow through something. Today we normally think about impermeable surfaces. Like an asphalt parking lot would be an impermeable surface. The water falls on that in the form of rain. And then when it tries to go somewhere, it has to be diverted off to a detention basin somewhere, perhaps. So that's an impermeable surface. And so you get the idea anyway. So permeability has to deal with the ability of fluids to flow through a subsurface medium. Now, you already know the term normal fault. Hanging wall moves down relative to a footwall. Okay, you know what a reverse fault is. These are all terms in petroleum, as it turns out, as well, not just in structural geology. So the hanging wall, you know what that is, and you know what the footwall is, of course. And then new terms that we're going to look at in here today, that would be petroleum exploration, people that go out and look for oil and gas. And there's a lot less of that looking for it anymore. We kind of know where it is now, because now we go to the source rock, or the petroleum source rock. And so petroleum source rock has some special qualities about it that make it a very good reservoir these days. And what we use to exploit that material is kind of controversial, so it's important that we look at it. So we're going to look at petroleum source rocks, and then burial, oil and gas maturation. Burial is pretty simple. You just bury the sediments. Oil and gas maturation has to deal with how deeply you bury organic-rich rocks, and those organic-rich rocks can then generate oil and gas at depth or at certain temperatures. So the deeper you go inside of the earth, of course, it gets warmer and warmer, right? And so the pressure becomes more and more also as you get deeper inside of the earth. So we're going to look at maturation, and then we're also going to look at these migrations of fluids. And so in the old scheme and how people used to find oil, they would look for the pathway, that you could have oil expelled from a petroleum source rock and accumulate somewhere else in a rock that we would call a reservoir. And so that reservoir, that's the Texas right there. So reservoir is the Texas pronunciation for this. And then seal. Seal is the rock that's deposited over the top of a reservoir that would be impermeable and allow that oil and gas to accumulate, and essentially is what's an inverted sort of bowl in the subsurface. And so you try to trap that material in the subsurface where you can then tap into it with drilling. And so a structural trap and a stratigraphic trap are just two types of trap that are associated with oil and gas production. Now, connate water. That's water trapped at the time of deposition, because most sedimentary rocks are deposited in the oceans. That happens to be salt water typically. So connate water is a byproduct, or one of the things that you also get when you drill for oil and gas. And so what do you do with that salt water once you've pumped it out of the earth? Well, oftentimes they actually re-inject it back into the subsurface. And that's where some of the issues today are with human-induced seismicity. Okay, so we're going to talk a little bit about that too. So connate water, that water that's trapped at the time of deposition. Water drive. If you think about oil and gas systems, we're really talking about something that is related to I oftentimes try to find metaphors for this, and so vinaigrette dressing is probably the best one. If you've ever had vinaigrette dressing, all it is simply some vinegar with oil floating on it, and then you shake it up, right? But that oil disperses and eventually recollects, and the oil floats on the water. You wouldn't want to pour it out and just have oil on your salad necessarily. You want some of the vinegar mixed with that olive oil, right? And so you shake it up in order to do that. But always remember that the vinegar, actually the oil floats on the vinegar, right? So the oil is lighter than vinegar. So density is really important with this because in the subsurface, oil is lighter than water and it'll float to the top. And of course, in all natural situations, if it possibly could, it would migrate all the way to the surface where it would become an oil or gas seep, actually. So gas is even lighter than crude oil. Natural gas would percolate right on through unless it was trapped at some point by some impermeable rocks. You have to have a seal, and then you also have to have a trap that will allow for an accumulation of that sort of material that is generated naturally. So that's what a water drive is, where the water is pushing up on the oil essentially and giving it pressure essentially, hydrostatic pressure from below. A gas cap, or they sometimes call it a free gas cap, and that would be the gas that could accumulate at the very top of a reservoir, natural gas that may accumulate at the very top of oil reservoir. Drilling is the technology we use to release oil and gas from the subsurface, and typically that's with a rotary bit. So a rotary bit these days typically has 3 cones on it. They call them tricones, and so you could actually spin that up, and what it does, it allows this to crush the rock essentially with a series of chisels on that rock. And by spinning it this way, you can actually have it make its way into the subsurface, drilling a hole, much like a drill bit does, right? So, but with 3 cones essentially that crack the rock and all. So that is rotary drilling. The rotary bit is the end at the bit at the bottom. And then you have also on that, you have jets that are down there that shoot drilling mud into that borehole. And all those rock cuttings that are crushed up down at the very bottom of a borehole tend to float on the relatively heavy drilling mud. So the drilling mud will be a little bit heavier than the water into which it's drilling, into the porous rock that it's drilling into, and it will float those rock bits up to the surface where they're called cuttings. And the cuttings are evaluated by a geologist in order to figure out exactly what the geology is in the subsurface, what you're drilling into. For the drill stem, now drill stem is a funny word, but it's really the pipe that gets threaded on piece after piece after piece. Sometimes it's 30 feet. I think sometimes they get 60 and 90, but it's usually 30-foot sort of increments that get added on to the drill stem. And so you may be drilling 6,000 feet inside of the earth or more. They can drill up to 25,000 feet commonly to search for oil and gas. At least in the old days they used to do that. I don't think they do that quite so much anymore, but instead, what they do these days is they drill laterally, and you still have to have drill stem attached to that rock, to the bit. And so as you're drilling laterally, you still have to have a drill stem. And so the drill stem is the pipe, essentially, that goes together to make that oil well. And if you think about it, in 30 feet, you can actually bend things that are relatively rigid in a distance. There's a certain sort of capacity to bend even metals, right? So that's what a drill stem is. The drilling mud, of course, is made out of barite. In the oil and gas business, they call it barite. Okay, so but barite is the mineral that you learned in the mineralogy part of this course. And so barite, together with bentonite. Bentonite is what they use for kitty litter, or you might call it oil dry even, right? And so you mix oil dry with water and then put some barite in there, and you've got a slurry of mud, or drilling mud in this case, that you can put into that borehole. It serves many purposes, actually. One of the purposes is to float the cuttings out of the borehole. The other one is to keep the bit, which develops a lot of friction down there, to keep it cool, right, and keep it from overheating and burning out, essentially, and wearing it out. It has diamond impregnated bits on either knobs or in chisel-like sort of formations at the end of that tricone bit. You want to keep it relatively cool. At the same time, you also want to lubricate it kind of, right? So that's cooling it and lubricating all the same process essentially. So that's what your drilling mud does for you. So it lifts the cuttings. It allows you to find out what's down there essentially. So casing is put at the surface all the way down to the bottom of the freshwater aquifer in order to protect the freshwater aquifers that may be in a place where you're drilling for oil and gas. They use casing also a little bit deeper sometimes. You may want to then put production tubing into if it's an oil well that's going to be producing oil, they put tubing into it, and then you can perforate that tubing in order to allow the oil to come into that drill pipe, and really it's the borehole that may have a tube in it. And so the oil then is produced out of that borehole. And so the oil accumulates in that borehole after a well is drilled, and then it is either flows to the surface under enough pressure, or it has to be pumped out of the Earth's surface in the subsurface in order to get it out of that, right? So the perforating is what they do in order to perforate they perforate the producing interval. And so you want to be able to produce oil and gas. And so you want to make the flow paths easy. So increase the permeability, essentially, increase the porosity just next to a borehole. So petroleum production is the process by which, after they have found the oil, then they begin to produce it. And so in that production, of course, then you have to take it to market in some way. In small oil fields in the past, they just used delivery trucks essentially to go out and pump the oil out of stock tanks. And so stock tanks would have both a mixture of oil and gas, oil and water, and the water would be siphoned off onto a separator, if you will. And so you'd have some salt water perhaps and some oil there. And they come along with, unlock the cap and everything, pull the oil, the crude oil out of that stock tank, and then take it to the refinery. And so that's one way they used to do it. If you have a large enough oil field, however, you can hook up directly to a pipeline. And so the pipeline will drain that oil field essentially and take it to a place where it can then be turned on and sent to a refinery by pipeline. So it's just kind of handy. So it depends on where you build your pipelines. Very commonly, you want to have pipelines running through oil fields so you can take it to market or take it to the refinery very easily that way. So that's the petroleum production side, and then you get the produced waters. We already talked about that a little bit. Connate water is often produced when you drill an oil well and then has to be injected back in. So the pipelines and the transportation are next, and then the refining process. And so typically in oil and gas industry, they call it upstream and downstream. So where you explore and produce that oil, that's considered to be upstream. Where you refine it and then take it to market, gas stations or any other sort of petrochemical sort of plants and so forth. That's the downstream side. And so the downstream side is the part that we experience as consumers, right? And so if you go to a gas station, fill up your gas tank, you're getting petroleum out of that has a octane rating. Octane is a organic molecule that it's refined. And so it has, 18 hydrogens and 8 carbons on it. And so when you break the bonds, that's when you actually produce the energy. And as you know, gasoline is very volatile. It's very dangerous, in fact, if you have an open flame around it. And so it will explode even. There's that much energy in petroleum products. And so that's what they do at refineries. And so that's why refinery positions can sometimes be kind of interesting jobs. Let me put it that way, because there's a habit for maybe cutting corners and trying to increase the profits at the expense of safety sometimes. I think that most refineries will say, no, that's not true. And I think that they have every intention of being very safe if they at all possibly can. But sometimes things wear out and mistakes are made. And so that happens too. So that is the pipelines and the transportation. Transportation is both just to get it to the refineries and then also from the refinery to the downstream market somewhere. So in the refining process, how do they do it? They do it through distillation. That's one of the ways that they do it anyway. And distilling something, they have long, tall towers, essentially, that will have various densities of product being driven off of a heated product. You heat it up a little bit at the bottom, and so different levels will correspond to the different densities of the organic molecules that are involved in crude oil. And so cracking is another term that is used in the refining business, and that's where they take some of the longer molecules and break them in half in a way they call it it's cracking catalysts. Okay, so catalysts are used then to make smaller and smaller, more profitable sorts of products out of petroleum. And so that's all of the terms right there. So let me explain, where does oil come from in the first place? And so that's pretty important. And I just discovered something. I got to share this with you. I discovered it's called whiteboard. It's I didn't know about it previously, but I have a tablet, and so I decided to make my own sketches today. So here you have sunshine shining on a water molecule that has some algae floating in it, and so there's your algae right there, and it's one single cell with multiple chloroplasts and maybe some multiple mitochondria, but the chloroplasts are in that cell membrane and with the nucleus that will help that organism, function properly. The chloroplasts are there to help convert sunshine and water to sugar, and it turns it into energy, essentially stores that energy, vacuoles and other sorts of things. And so that's some green algae on the right-hand side of this image right here. But just to show you, that is where most oil comes from. It comes from algae, okay? Or it comes from leaf debris and anything that is a living organic molecule. When it lives and then it dies and then gets buried, it has the potential of producing oil and gas. Okay, so technically you probably could get some oil out of dinosaurs, but not bloody likely, because there's a lot more algae on this planet than there have ever been dinosaurs. Even though they say there were billions of T-Rex, they're talking about the millions, tens of millions, hundreds of millions that T-Rex was around, right? And so, yeah, of course you're going to have lots of them. So you have algae floating in water, and it's floating up there, making its own energy and everything. So it lives and lives and lives and lives and lives, and then it finally expires. When it expires, it falls to the seafloor, and there it may get buried by sediment. And so sediment, together with the organic remains of all of these sea organisms, would accumulate on the seafloor, and sediment would continue to rain down in the oceans. And so if you have enough organic material in a mudstone, you could potentially have what we refer to as a petroleum source rock. As it turns out, there's really three main types of petroleum source rock. Four if you want to include coal. Coal can actually produce methane as well, but we don't want to usually talk about it as a petroleum source rock. Normally, we talk about black shale. Black shale is the most common petroleum source rock. It's what they produce out of now in places like North Texas, in eastern Oklahoma. They produce out of it in the Bakken Shale up in North Dakota. So all of these major oil fields that you may have heard about over the last 10 years that have been developed. They said that at one point there was a new millionaire every single day in North Dakota. I think that was during the main push for this last oil boom that they've had up there. But the Bakken Shale is an organic rich black shale. And so black shale, the black color comes from all the organic material in it. That's the color of carbon, essentially. So if you have carbon and you have black coals, those are things that are rich in organics. And so you can also have mudstone. It doesn't have to have the facility. You remember, facility is the ability to split into plates for shale. So shale is a type of mudstone that has facility. But in fact, if it's just an organic rich mudstone, that'll work too. And so if you have an organic rich limestone, any organic rich rock potentially could become a petroleum source rock. It's just that the most common one is in fact black shale. And so black shale is a good petroleum source rock usually. So oil is not from dinosaurs typically, okay? I just explained why, right? But any living organism that lives and dies can accumulate in a certain place. And those are carbon-based life forms. Everything that we have on this planet so far is carbon-based. Even if it's a sulfur-fixing bacterium, it is still carbon-based. And when it lives and dies, that carbon goes somewhere. It's part of the larger carbon cycle. And so living organisms eventually end their existence and they'll fall and they'll accumulate. When they accumulate in sedimentary rocks like this, I'm showing you a water column where these things have fallen down to the seafloor essentially here. Those things become what we call mackerels. And so mackerels would be, all those things that were once living, the lipids, the carbohydrates, the proteins, everything within that living organism becomes a mackerel. So I want you to think about mackerels like a mineral in a rock. So if you had a mineral in a metamorphic rock, or if you had a mineral in an igneous rock, mackerels are organic molecules that are in sedimentary rock. And so sedimentary rock can include things like liponite or vitrinite or inertinite. Inertinite means that it doesn't react much. And so, in fact, it won't generate any of the petroleum products that we're used to. So inertinite is kind of what we would, it's already past its usefulness for generating oil and gas, but some other mackerels are not so much. The liponites especially are pretty good for generating oil and gas. And in fact, there's a special variety of mackerel liponites that they're known as kerogens. Kerogen, you've heard the term kerosene before, right? But kerogens have these complex organic molecules in them, and they generate oil and gas once they're exposed to heat and pressure. And so some of those liponites are kerogens, and those kerogens would include things like resinite, resin from trees perhaps, pollen, things like that. Sporonite, so many organisms put out spores rather than seeds, and those spores could then generate oil and gas as a type of kerogen. So sporonite is a variety of kerogen. Cutinite, organic molecules, they make their cell walls sometimes out of cutin. It's a little bit tougher molecule, so the water has it's more water friendly, I guess you could say, to retain water in the cell. So cutin is that sort of substance right there. Alginite from algae, of course. And there's other ones too. There's like 3 or 4 other important kerogen producing sorts of materials. Okay, so there's like 4 different types of kerogens. You don't need to know this for this course, but my petroleum geology course, they need to know it. And so they just call it type 1, type 2, type 3, and type 4. But those 4 types of kerogens produce different types of products, essentially. And alginite is really good for producing crude oil. And so crude oil is one of the best things you can get out of alginite. And so if we look at these petroleum source rocks, we're going to bury them even more. And as you keep burying them, it becomes, in that burial process, you're also getting it hotter. Okay, so you're getting a geothermal gradient, and you're essentially cooking those petroleum source rocks. And so as they get cooked, it generates, these kerogens will actually cook into natural gas and petroleum products, if you will. At least 3 types of them will. And of course, when you light a match next to a petroleum rich sort of thing, it'll catch on fire, right? And so, in fact, you're breaking bonds when you light it on fire. And so you don't want to do that around gasoline because it will hurt you, okay? Gasoline explodes when you have an open flame next to it. So that is the thing that happens in the subsurface as you cause it to go through this process we call maturation. So with deeper burial, you're cooking it. You cook the oil first, because those are the complex the complex kerogens and the complex molecules that may be very lengthy chains. If they get much past, I think it's 30 or so, they become kind of waxy, but there's natural waxes that are generated by the earth. But the very lightest ones, the very last products that tend to be generated as you bury these rocks is the natural gas, and that's CH4 is the most common component, in fact, of natural gas, and that is the hydrocarbon known as methane. So methane, we're going to talk about methane later on when we talk about climate change as well, but methane. So remember that oil and natural gas, those are 2 varieties of petroleum. So we're going to look at petroleum now. So when you bury these rocks, in this case, I've actually shown you what it's like to have folded rocks. Okay, so in this image, I'm trying to push in and fold those straight a little bit. And you can see anticlines and synclines on here. Well, that oil that was generated in that petroleum source rock, once it's buried to a certain depth and a temperature, it goes through a certain transformation. So that shale that's down there, the clay minerals in that shale actually go through a transformation You don't need to know what it is, but it's a schmectite to an illite, just so that you've heard it now, but you don't need to commit it to memory. But it's a certain transformation. And when you go from a schmectite to an illite, you actually release water. And when you release that water, it actually releases the oil as well. And so the oil actually gets expelled from that petroleum source rock at some point. Commonly, it gets expelled from that petroleum source rock if it's a mature rock. And so you expel some of that oil. What happens to it? Well, it begins to migrate. It finds its way through the vinaigrette bottle upward. And it percolates upward through these pore spaces, little tiny openings in the sedimentary rock that's there that otherwise would be full of water. It displaces the water, pushes the water out of the way, and the oil flows upward. And here I show you that it flows upward until it just can't flow any farther upward, because it runs into an impermeable rock that we know as a seal. So a seal is over the top of a place where that oil would accumulate. The oil itself accumulates in what we call a reservoir, or reservoir if you're in Texas. And so that reservoir will contain, it's really an upside down bowl, if you will, or an upside down ridge, if you will, of material that is covered by impermeable rocks above. So that's your seal over the top. And into that sort of surface like this, it's called a trap. And so the trap itself is the anticline, but the seal is the shale that's in that anticline that is just above that reservoir. And so here you can see the oil is in a sort of like mushroom shape or a sort of cap at the top of these anticlines. That's why structure is really important in oil and gas production. And so people look for anticlines. They have looked for that for over 100 years in order to produce oil and gas. And so in this process, remember, the oil is floating through the water to begin with, right? But eventually, when it can't get any farther, that water is pushing upward on it, right? So there's hydrostatic pressure in that pore space that's pushing upward. Impermeable at the top, but permeable down below that allows the fluids to flow through the rocks there and into that reservoir. And we're still getting heat at this time too, right? So this is still buried rock. So your petroleum source rock is down there still generating oil and gas if it's at the magic zone. And that magic zone is what we in fact call the oil window. And so that corresponds to roughly 65 to 120 degrees centigrade. Okay, so centigrade's what we're using for this scale, and that corresponds to roughly 2,000 to 5,000 meters, or 6,000 to about 15,000 feet. You will be generating oil out of a petroleum source rock. That's good to know. So you have to drill a ways in order to produce oil and gas, typically, unless it's already made its way to the surface and becomes an oil and gas seep, right? So the oil is expelled. The water helps expel it when it has that sort of shale clay mineral transformation from a smectite to an illite. So that water also is released and will find its way out of that petroleum source rock. Notice that you don't have any accumulation in the syncline here, but the accumulations, in fact, are in the anticlines here because they're upside down containers, upside down bowl, if you will. So basins can also have oil, but it's always going to be at the perimeter where you finally reach. The oil will migrate up dip and into the margins of a basin. In a dome, it tries to migrate to the top of that dome if it possibly can. So that's the nature of oil. It will migrate once it's in the subsurface and released to flow. So that is the oil window here at between 65 and 120, or 2,000 to 5,000 meters. Now, where does the gas come from? You're probably wondering. It's like, well, the gas is generated last because that's the simplest molecule. If you're cooking something, the last dregs of that cooking are the CH4. It's the simplest molecule. You've already broken down all the complex carbohydrates, lipids, and all that sort of thing, right? And so finally, between 120 degrees centigrade and 250 degrees centigrade, that typically occurs at 3,000 to 6,000 meters, or 9,000 to 18,000 feet. That's called the gas window. And so when gas is generated, so all of your oil has already been generated and has migrated away at that point. And so they're looking for gas now. And so here's the gas. What does it do? Well, it follows the same pathways. It'll follow up into those reservoirs at the same time and be bound up below a seal of some sort in a trap. And so the trap is the structure, the seal is the overlying rock, and the reservoir is where things accumulate, right? And in each one of these diagrams, what I've tried to do is project the oil as a green color, and that's typically what petroleum businesses do. Green means oil, red means natural gas. And so the green here is the oil, and the gas actually migrates up not only through the water that may be in that water drive, because gas is much lighter than water, right? If crude oil is a little bit lighter than water, typically it is anyway, it'll migrate up through it, and then your gas can easily migrate up through it as a smaller molecule. And so it migrates up through this and it accumulates then at the very top of that oil reservoir. And so you have that impermeable rock at the top up there that keeps it from going any farther up. So that's your free gas cap there. You know, a free gas cap forming at the top of an oil reservoir here. And so that going into the gas window generates the last little bit out of those kerogens. After that, very commonly, you will have inertinite. And so it's not going to react anymore to heat and pressure. And so here is your gas window. Finally, you've generated all the oil and gas out of this substance. And so how do these things accumulate? So this is where the structural part of geology and the stratigraphy part of geology is pretty important. And so for the longest time, oil and gas has been the realm for geologists, and so we know how to map the surface, and then we also know how to map the subsurface. So we're able to figure things out three-dimensionally. And so that structural aspect becomes really important then. Here you see a couple of anticlines and a syncline in the gas window here. Here's a couple of an anticline paired with a syncline here, and you can see where the oil has occurred here. And so they've drilled a few oil wells here. They've drilled through the gas. Now, typically they try to miss the gas if at all possible. Oil is a lot more expensive than gas, as it turns out. It's a much more valuable product, in other words. So natural gas, unless you have a market or a pipeline nearby, gas is usually more of a hindrance than it is a help, in fact. And so even though it's rich in BTUs, if you don't have a market for it, it's useless. And so very commonly in oil fields, they actually just light it up and they flare off the natural gas. And it's like, and you're probably going, what a waste. Yes, it is. It's an enormous waste. And it pollutes at the same time. So when you flare methane, that's an issue. So, there are processes. They're very expensive processes is the only issue. Everything's driven by economics, as it turns out. And so in many oil fields, they just flare off the natural gas. If they can, they try to capture it and then take it to market. But you're talking about $2.20 for billion cubic feet, I think it is. I think that's the current rate right now. For oil, oil is like 60-some dollars a barrel for 42 gallons, right? So it's much more profitable. $2 versus $60. Yeah, not. It's going to be the oil that people mostly go for. So here you can see this oil field where they've drilled several of the wells here, and they try to penetrate into at least the top of that oil producing interval here. And you can see that one of them is at the top of an anticline, like we've already discussed, and I've shown you that sort of imagery before with the green and maybe even a gas cap at the top, and that's what they're showing here. That's the free gas cap at the top of that. And they're also showing you a fault here, and so that's another type of structural trap. This is a structural trap called a fault trap, as opposed to an anticline trap. Well, fault displaces the rocks, and you can see that this has the hanging wall moving down relative to the footwall. The footwall's on the left-hand side, the hanging wall's on the right-hand side, but they're showing you impermeable rocks up against that fault zone there, and it's stopping the oil and gas from migrating farther up dip. On the other side, it did migrate up dip, and it made it all the way to the surface where they show you an oil seep, right? So the oil is being produced out of that, they call it a source bed. It's petroleum source rock. And the petroleum source rock also generated the oil and gas, and it percolates through the sandstone here. But when it got that that impermeable layer, which is a shale above that. Those are the dashed lines in that tan sort of unit there below the surface, right? There's an oil well penetrating into that oil there. So that's a rotary rig that would have drilled into that reservoir and produces out of a vertical well there. And they're showing a free gas cap on that one, but they've missed the gas, luckily, there, so they don't have to flare it off. There's several other oil fields on here. Another one that's related to that fault structure there, you can see farther up, and then you can see other oil in here, other oil wells. Those are actually just drilling rigs right there. Those are pump jacks, actually, they're showing at the surface also on either side of the oil rig that's in the front on the right-hand side there. So those are pump jacks where you actually have to siphon the oil up out of the subsurface, out of the borehole. Two different types of structural traps here, and shows you what an oil seep is. We talked about oil seeps when we talked about Azerbaijan and the fountain of oil, right? And we talked about a gas seep when we looked at Yanar Dag, that place where natural gas escapes and then was struck by lightning perhaps at some point. So that is two types of structural trap right here. You can also have domes too. Here's a structural dome right here, but it's actually related to a salt dome. So the salt has been mobilized, right? Remember, salt is less dense than the rocks that typically bury it, and so the salt has penetrated through those rocks in a process called diapirism. You don't need to know about it, but it just pushes its way in, breaks those rocks up, and then, of course, the oil is still going to migrate up dip. That's one of the key things. Oil will migrate up dip as much as it can. And so here you can see two oil fields on the right-hand side, two oil fields on the left-hand, well, two oil fields on the left-hand side, and then there's an oil field at the very top up there that's over the top of that salt dome. And so that salt dome, they're producing just out of the top up there. I think the reason they do that is because that's what Spindletop was. It was in a situation like that where they produced right out of the top of a salt dome like that. Three types of structural traps: faults, anticlines, and salt domes. And domes in general, in fact, can produce oil and gas in the up-dip beds around them. A little bit more complex, and it took a little bit longer to find these sorts of features, but these are called stratigraphic traps. And so stratigraphic traps very commonly are associated with unconformities or pinch outs. Sandstone could be deposited at the same time as a shale, perhaps, and you could have that sandstone pinch out eventually. And so if there's oil and gas that has entered into that sandstone, it's going to migrate up dip until it can no longer migrate because of the impermeable rocks around it. And so that's a pinch out, the second one here. The top one up there is an unconformity. And then lastly, they show you a reef on the right-hand side. Now, reefs are usually carbonates, right? And so in that carbonate, they're typically made out of dolomite, and dolomite is a very good reservoir rock in reefs. And so you can see that that reef itself has a lot of porosity in it. And so oil and gas, which would have migrated from perhaps in a deeper setting. And so during the maturation process and the migration of that oil and gas out of a deeper basin, perhaps it would have migrated into that sort of structure. And well, actually, it's a stratigraphic trap, but reefs are really a type of organic structure, if you will. And so that's where you can produce oil and gas out of as well in a stratigraphic trap. So three types of structural traps, three types of stratigraphic traps, two different kinds of traps in general, right? So stratigraphic and structural, but in fact, each one of those has three subcategories. And so I want to show you next how you would go about drilling one of these things. Okay, so I don't have all of the diagrams on here. I probably will have at some point, but when I discovered whiteboard, it's like, well, I can actually draw like I'm on a board and just take a snapshot of it and show it to you. This makes life a little simpler for me because you rack your brain and how do you teach certain topics, right? Well, this is how I'm teaching this one now. And so what you see here is a rotary rig at the surface, and so that's what they call an oil derrick also. So that rotary rig has a drilling platform, and they spin the drill stem up, and then attached to the end of that is, of course, that bit, and the bit drills into the rock down below. And it takes usually about 60 days to drill an oil well, I think. Now, it depends on how deep it goes, of course. You can drill some, in a day practically if they're only a few hundred feet deep. And there are a few fields that are only a few hundred feet deep, places like the Illinois Basin and all. It's a pretty mature field, so all of that shallow oil has pretty much been produced, but not all of it yet, I'm pretty sure. So here I show you an unconformity, but then below that I show you some folded strata. So in this, the anticlines are actually the traps, and you can see 3 separate accumulations there, and they've drilled into one of them. It doesn't have a free gas cap, so you don't have to worry about flaring off the gas on this one. But, potentially you could actually have some oil trapped in that unconformity as well. So here is a typical explanation for what it is to have conventional oil exploration. That's a technique that people have used for about a century, and so a little over a century now. So 1859, the first well in the first well in the U.S. anyway. And so here we are in 2021. This is not how we find oil and gas anymore. So I got to show you how that happens. But first, I need to tell you a few more terms. Okay, so here's a few more terms to remember. Some of these you're already familiar with. You know what shale is. You know what facility is. That's the ability for shale to split into those sort of flakes, right? You know what a reservoir is. We just talked about that. You know what quartz sand is, right? So sandstone's made out of quartz usually. And you can have lithic fragments also, and maybe some feldspars, but typically a good quartz-rich sand. You can go out and you can mine that stuff now. They do it in Missouri now, right around St. Louis. They have sand mines, and those sand mines actually produce what we call frac sand. And so places around Pacific, Union, Arnold, Festus, towns like that on the southwest side of St. Louis actually produce out of the St. Peter sandstone. St. Peter sandstone is very easily broken up in just your hand, and so it's a very convenient sort of source for what we call frac sand. So if you think about it, those kerogens are down in the subsurface generating oil and gas in a petroleum reservoir. And when they go through that process of maturation, not everything migrates. First of all, not every shale is just shale. It may have layers of sand in it. It may have other, layers of carbonate in it as well. And so that oil first goes into those beds, and they call them carrier beds very commonly, and so into those carrier beds. But then, if you think about it, a fair amount of the oil that has not been expelled, there's a fair amount that's still residual in that shale that never was expelled from it. And so even though it may be at depth, it may have generated oil already, how can you go down and explore for that? Well, that's what George Mitchell did, right? So he tried it 8 times, and on the 8th time he succeeded. So what he did is he drilled laterally. And so he turned the drill bit on its side and was able to continue drilling laterally. And as he drilled laterally, he recognizes, like, we're drilling through some really oil-rich rock. How are we going to be able to produce out of this? And so what they decided is once they took the drill stem out of the borehole, they put in production tubing, and then they shot off little charges in there to penetrate through the tubing. And then they began to pump fluids into the subsurface, and they hydraulically fractured that rock. So under high pressure, that borehole begins to expand and generates fractures that penetrate into the source rock. And then what happens is the oil will make its way into the borehole from those fractures and fill up that borehole eventually with oil. And so then they produce that oil out of that horizontal bore like that. So sand, in fact, is what they call a proppant. When they inject the fluids into the subsurface, they also may mix in some diesel. They could mix in some other quote-unquote proprietary products. Well, it's below the drinking water sort of level, and so they don't worry about it too much, and so they inject that water into the subsurface, fracture the rock there. They pump in the proppants then on sand trucks, and they'll mix it in a slurry, and the sand is there to keep those fractures open, so the sand will enter into those fractures under high pressure. And so they produce oil and gas after that. And so why don't you watch a video? It might be easier. If you just did fracking in YouTube and did a search on that, you would see how it's done with very slick animations, not the crude ones that I'm showing you here. But at the same time, I think I'm fairly accurate in how they do it, okay? So that is the story of unconventional oil, shale oil, they call it, unconventional resources. And so here is one more cartoon that I draw. They pull out the They remove the drill rig completely, in fact, and they take out the drill stem, of course, and then they inject it with these fracking fluids and the sand, which is the proppant. And those fractures stay open, and then the oil drains back into the borehole and then is produced at the surface. So, again, they've bypassed the typical anticlines in this case, and so what they're really looking for is the anticlines that are within that petroleum source rock, and so structure still plays a role in how you would produce in an unconventional oil exploration technique. So this is what we call today shale oil. Not to be confused with something that was known as oil shale. Now, oil shale is today being produced for shale oil, as it turns out. I have my petroleum geology class on a project in the Uinta Basin. It's in Utah, and there's all sorts of drilling logs, and there are great records for all of the wells. And so we're looking at a little 2 square mile area in petroleum geology and trying to understand, is like, why are they producing it this way when they could have been producing it? Well, they are going to produce it eventually with horizontal drilling like this. So, so the fractures allow the oil and gas to escape and then releases it. And so that's the story of unconventional oil exploration and production. And they call the whole technique, that whole play is called shale oil. In the beginning, and this is actually what George Mitchell originally had done, he actually did shale gas to begin with, and around the Dallas-Fort Worth area. He produced out of a rock unit called the Barnett Shale. Well, it had been matured enough so it was actually producing gas, and he realized that at the time, at least when he was producing this, the gas was through the roof. Oil was pretty much through the roof, and then other companies began to see, is like, wow, he hit on this, didn't he? And they didn't want to miss out on this, and so all the major oil companies decided to adopt this new technique. Okay, so if you know that there's been this history of oil production mostly in the Middle East, but if you looked at where the oil actually occurs, it's pretty much all over the world. Okay, it's in Indonesia, well, particularly in that part of Asia anyway, and certainly in Central Asia and Kazakhstan and places like that. What they have not done through the rest of the world is they have not applied this technique to it so much. Now, it's being used in China now to develop some of the oil fields there. It's being used in not the Middle East yet. As far as I know, it's not, because there's so much undiscovered oil still in the Middle East in conventional reservoirs. And conventional reservoirs could still be drilled horizontally like this in order to produce oil and gas. And so, in fact, we're looking at least 300 or perhaps more years of oil production on this planet. And you could either look at that as a blessing for this, society that we live in, or a curse, because the oil and gas that we produce is problematic because it gets burned. And when you burn oil and gas, whether you're flaring it off or you're putting it in a pipeline, it's eventually going to be burned. It'll be stored for a little while and then you burn it, right? And so the oil that's produced at refineries, it eventually goes into stock tanks, and those stock tanks deliver the materials, especially in wintertime. It keeps people warm in places like the East Coast, the heating oil and all that, right? And it keeps the trucks running that deliver the goods all across our country. But if you think about it, it's like all of that winds up in the atmosphere. What was once in the atmosphere as gas, or gas saturated in the water, that was being, the photosynthetic sort of organisms, the algae would take in carbon dioxide and water and produce, with sunlight, and they would photosynthesize and produce sugars for that organism. All of a sudden, that became a commodity back in the mid to late 1800s. And then it became commodity again when we look at the transportation revolution that's occurred in the last 100 years here, roughly. We have altered Earth's climate. I don't think there's any dispute about that. Every scientist agrees about that. Not everybody thinks it's a bad thing necessarily. I don't think that that's very forward thinking. It's easy to be in Missouri and say, well, what do I care about global warming? Because seas aren't going to make it up here, but they will make it into North Carolina, South Carolina, Florida, Georgia, Alabama. They're going to make it all to the eastern coast, and cities will have to move. And people around the world will have to, people that have never driven an automobile, that never produced any oil, or, any of the sort of like contaminants that get into the atmosphere. None of that carbon dioxide, right? None of the methane that gets released from some of these oil fields. They don't flare it all off. Some of it escapes. And so it is a product that causes an excess of atmospheric heating. So we're going to look at climate again too. And so, but if we look at oil is a very seductive field for geologists. They pay very well. So geologists tend to, maybe turn a blind eye sometimes to this. As an instructor, I can't do that. It's like we have consequences associated with the production of oil and gas. It's not a matter of if it is. Of course it is. Yes, we have a byproduct that's produced and through the work of geologists, So it's like, so what do we do about it? Well, I think most geologists you will find are very pragmatic people. So I think that there is a lot of support even among geologists. And I think even large corporations now, they see the writing on the wall and they say, how can we help to address this? And of course, they use it in their marketing all the time. BP, we're the friendly company for the environment. All those sorts of things, right? Well, they had the largest oil spill on Earth. But it's like, how do we clean this up? How do we make this a planet that is good for us and good for our children, good for our grandchildren and our great-grandchildren? And so that's the issue, I think, is like, how do we make this a sustainable planet? Let's stop thinking about going somewhere else, even though I think that's still a valid hypothesis. We need to explore space, but we also need to take care of our planet too. Okay, so there's two parts that we have to do. So in order to do that, you got to be a good citizen. You have to know things. You should be educated, right? You can't just like turn everything loose and say, let the market decide everything. It's like, we need to be careful. We need to be careful about how we produce oil and gas. And, it's a double-edged sword. We use it for some of the best things in the world. It goes into the hospitals to heat the hospitals. It makes the products that they use in the hospitals. It saves lives. And it transports goods to people that otherwise would go hungry in wintertime. You have to know that. But at the same time, there's a longer term consequence to our use. And so that's what I'm concerned about now, and I'm going to always probably be concerned about this. I know how to produce oil and gas. I know how it's done, and it can be done. It can be done effectively, and you can do it carefully, okay? But it's going to take regulation in order to do that. And so it's a very scary world that we are in, precarious at the time. How much are we in this altogether is the question, right? So if you'll recall from the last presentation on energy resources, whaling was the number one product that's the number one way that we got whale oil in order to burn it in lamps 200 years ago. So what do we do now? Well, we flip on a light switch. And today we got LED lights that will light up for pennies for a day. It's like we didn't have that 10 years ago even, right? So technology is making it a better world in some ways. And so we have to think, it's like, But what's it going to be like in the future? What's going to happen to the human race? I mean, that's what we're really concerned about. When we talk about saving the earth, really, it's not saving the earth, it's saving the human race. Because we have so many people on this planet. We got 8 billion people here now. And it's going to double in 30 years. So by 2050, we're going to have 16 billion people on this planet. Something has to be done. We used to think that we only had 60 or 90 years of petroleum left, but now we got 300 years. If only in 30 years we're going to have double the population, think about having double the cars on the highway, right? Well, they better be electric by then, I'm hoping anyway. It's like, we got to get smart about this, right? The petroleum-based transportation system has gone with a free market, and that's probably going to change. So in the future, we're looking at electrical vehicles. We're still going to have some oil burning vehicles. There's places you cannot get to unless you have some sort of oil burning vehicle. So maybe hybrids and things like that will actually help to replace the gas guzzling vehicles that we have right now, the fuel guzzling trucks that we have on the highway, and the fuel guzzling airplanes. And they're all getting better. The technology is making it possible to get better and better fuel efficiencies for every product that we use. But we're going to have to start generating things with solar energy or nuclear energy. We're going to have a groundswell of public push, and people, as soon as one of the things I've noticed since last November, right? So last November, people saying, well, the gas prices are going up again. It's like, well, yeah, they are. Is that a bad thing necessarily? They pay 4 times what we pay in the United States and Europe and places in the East, I'm sure. They pay a lot more than what we pay here in the United States. We have cheap oil and gas. There's no doubt about it. Shouldn't that be helping subsidize the effort to get things switched over to a more economical and / sustainable sort of like future for us? So, okay, off my soapbox now. I want to tell you a little bit about petroleum geology and energy resources, because geology and energy resources are like this. If it's not coal, you already know that we're turning away from coal. We've turned our back on coal pretty much. And coal, even the coal industry recognizes that now. It's like, well, you don't want to be in a place that is going to have a vanishing career path for you, right? If you're a coal miner right now, you better start going to community college or college of some sort in order to get retrained to do something else, because coal mining it'll be around for a while. We still have to produce steel. We have some other products that we need to produce as well. But coal is not going to be a long-term sustainable sort of like future for most people. We have to look to the future. If you don't look to the future, who's going to? Okay, so we're going to talk a little bit about emissions next. We're going to talk about climate change and what's human-induced climate change. But for now, that's it. And so I should have 3 presentations. Hopefully by Friday, I'll have the 3rd one uploaded on climate. There's some interesting stuff in there. Yes, climate change occurs naturally. We're going to talk a little bit about that as well. So, so just a little bit of a teaser for that. So climate change is important, though. Anyway, thanks for your attention, and thanks for going through this part, a really important part, practical part of energy and sustainable resources. Thanks. Bye now.